Hi everybody, welcome to attend our presentations of Evilsploit, a universal hardware hacking toolkit. Today we are going to show all the details about this and why so special about this. We will talk about the potentials of this little toolkit in some out-of-the-box application too. First of all, we all know about the hardware hacking and how messy to start hacking to the hardware. You need to study the hardware to find a way to get the software and hack it. When we mention to get the software, means majority of the hardware are run by the software itself. There are quite some misunderstanding from the software. Hold on. From the software-oriented hacker to assume the hardware hacking is all about to hack the firmware or software. However, it's more than that. A hardware can also run by itself with its own digital logics. Hold on. Alex? How can I move my cursor here?
Is your mouse not working? This isn't touchscreen, is it?
No.
Okay,
I can see. I can see. Thanks. For both of the scenario, the hardware will usually come with the provisioning ports, except those extra small form factors, things such as a smart card. By making use with the provisioning port, a hardware hacker can control and do everything to the hardware in different ways, such as to dump the firmware, to write new firmware to the hardware, and to debug the hardware. Well, by making a simple assumptions that majority of hardware having provisioning ports, then it is crucial for most hardware hackers to find out. As mentioned earlier, most hardware are run by software. And once the provisioning port is identified, then a hardware hacker can harness it from identifying the bugs to the developing reliable exploit to the hardware. However, since majority of the hardware hackers are software-oriented people, it's just a little bit unfriendly to deal with the multimeter, oscilloscope, datasheet, and PCB board layout to search for the provisioning ports. In fact, it's really prone to the human error to memorize which pin come with what features, which pin number should connect to which another, and which color of cable represent which pin number. Please ask yourself how often you make such a simple mistake while doing the hardware hacking in daily basis. On the other hand, most hardware hacking literature are still demanding or assuming a reader to understand what are TX, RX, ground, or even the TMS, TDI, TDO, or TCK. Yes, it's really unfriendly. So the question right now is it compulsory to understand those nasty things in order to hack a hardware? Try to imagine if a special cable, which one end is connecting to your computer's USB port and another end connecting to the target hardware with a special connector, then from Minicom, PUTTY, URJTAG, or OpenOCD point of view, is it still compulsory to understand those complicated things? The issue is just like we never need to understand how the ECU works in a car in order to let us to drive a car. And that's why the car hacking issue get into the place. So the intention of our Evilsploit here is the special cable that I mentioned earlier to allow everybody who interested to hack a hardware can have the most beautiful experience in the first try. Forget about all the TXRX things. Forget about pin number, forget about whatever color of the jumper cable should connect to which pin. Now, simply build the connections to those suspected pins that you believe is the provisioning port, and then the Evilsploit will do all the rest of the nasty things for you. After that, fire up the Minicom or Open OCD. The target hardware is ready for you, and here you go. Well, let's start with the slide. Who we are? I'm Chui, a system architect, and this is Mr. Wan, a senior engineer. We start from the introduction to the hardware hacking, and we define the hardware hacking is to understand the inner working mechanism of a piece of hardware or a group of hardware where connected each other in wired or wireless way. This is a small system, maybe. Reversing is the core of the hardware hacking, and it can break down into static and dynamic way. This is a further breakdown of the hardware reversing methods. In general, we need three things to start hardware hacking: hardware-related things, firmware, and provisioning ports. The key point here is crucial to harness the provisioning ports in order to hack a hardware. So we have three objectives today: to automate the process of finding provisioning ports, to manipulate the provisioning ports being found directly, to maximize the automation level of the hardware hacking process. This is our three objectives. And then we have three problem statements here. First, we need two sets of the tools for bus identification and manipulations. Second, we need to wire up the connection for 2 times manually. Third, with such a gap between the bus identification and manipulations, we cannot automate the process of the hardware hacking. It's impossible. As a new proposal to the hardware hacking, we use a connection matrix to bridge the gap between bus identification and bus manipulations. And then we use a bus interfacing chip to emulate and communicate with the target. After that, we use a controller to manage the synchronous control between the connection matrix and bus interfacing chip. And finally, we use a computer to automate the process of the hardware hacking in high level. Now, what is connection matrix? We see a new term here, connection matrix, but what actually the connection matrix is and why we need it. We start from the why. For something that seems similar to the connection matrix, we have multiplexer, the combination of the voltage translator and FPGA, or keep doing the routine job manually. You connect the jumper cable, keep doing it. However, it seems all of them are not perfect, and that's why the connection matrix get into the game right now. Now, what is connection matrix? Connection matrix is a device which can provide arbitrary physical connection routing between inputs and the outputs. It's a well-known technology being used in the large-scale audio distribution systems such as public address for years. It manages the connection in analog way, but not the digital way. So it has all the characteristics of the analog connections, but being able to be controlled via the digital communication bus. Connection matrix can be implemented by using AD75019 from ADI. And this is a general purpose version of AD8113, which is widely being used in audiovisual industry. It consists of 256 analog switches to implement a 16 by 16 analog array. And as mentioned earlier, all connections are in analog way, not digital. Multiple AD75019 can be cascaded, but this is a little bit ugly, like this. Well, let us represent the connection matrix in the form of matrix, as what we usually see. From the diagram, we can see that the input 2 and 5 are connected to output 5 and 3 respectively. All the rest are not connected. Simple. Now, we can disconnect the input 5 from output 3 in runtime, but keep the state remain, which means it can be connected again from time to time. Such a characteristic is useful to detect and rule out the reset pin from affecting the bus identification process of our Evilsploit. So, the diagram now became input 3 and 5 are combined and they are both connected to output 3. This characteristic is useful to pull multiple pins to the ground or VCC all together. Regarding the connections in analog way, output 3 and 5 can be used as input and lets the input 5 at outputs. The second diagram here is in fact similar to the first diagram, but in reverse directions. Such a characteristic is useful to tap and bypass the impedance monitor or EOL protected pins. About the expandability, multiple matrices can be cascaded as mentioned earlier in general. However, in specific, the real case scenario can make things more complicated. From this diagram, the route where matrix 0 and matrix 1 detect a suspected impedance monitor pin, then the connection where matrix 1 can be disconnected. Then matrix 0 will route to matrix 2 to take place of matrix 1 in tapping the impedance monitor pin. Since the source follower provides infinity impedance at the input, then the countermeasure is bypassed and the whole process can be automated. It's really hard to build this with a multiplexer. Let's see some real signal from the oscilloscope. The yellow signal is an input signal and it's a square wave. The voltage level is 1.84 volt. And how about the outputs? The blue signal is the outputs. We can see that it's almost identical to the input signals. Their frequency is 2.06 megahertz, and there's no significant delay or jitter found. Since they are square wave, they comprise a number of odd harmonics. Since the input square wave maintains its shape at the outputs, the bandwidth of the connection matrix is higher than 2.06 megahertz. Let's try with higher frequency. In higher frequencies, it seems that the voltage drop getting higher. We intentionally increase the amplitude to 3.20 volt to make the result clearer. From the result at the right hand side, we can see that the output voltage became 3.12 volt now. If we zoom into the result, we can see that the frequency is about 14.7 megahertz, and again, no significant delay or jitter found. However, the shape is slightly degraded. This is in fact the TCK signal from a JTAG connections, and the JTAG bus still managed to work improper. Now, if we go further, how about we let two signals with 2 MHz and 15 MHz being connected to the connection matrix in simultaneous way? Fortunately, the results are about the same, so we can assume the connections are nicely isolated each other. This slide is a little bit precautions for the beginner. From the result, we can see that the output signal is degraded apparently. While being connected with JTAG, it's just not working. Once detached from the probe, it works again. It's strange, but why? Check the columns of the input impedance from this table. For 1 times probe, it is 100 picofarads. For 10 times passive probe is about 13 picofarad. And for 1 times or 10 times switchable probe, its input impedance is about 110 or 16 picofarad respectively. So by simply switch the probe from 1 times to 10 times, we solve the problem for whatever probe you have. Try it. Now the discussion get into what is bus interfacing chip. The bus interfacing chips are normally off the shelf from the manufacturer. It's playing the role as an agent between the computer and the target with standard communication bus. With this, we no need to do bit bang. The chip will generate appropriate control signal with better signal integrity and timing for you. And this is normally controlled by the USB interface. What is microcontroller? We just skip this slide, it's too simple. So, this is the system diagram of the Evilsploit. The computer will determine the routing pattern of the connection matrix via the control channel bus, which is the right-hand side. The connection matrix can be expanded or cascaded. The computer will communicate with the target via the communication channel bus. The connection matrix allows arbitrary permutations of routing pattern for the computer to get access to the target. This is the fundamental diagram of the Evilsploit. So, with Evilsploit, something special can happen. By repeating two-step tasks, which is the first step to set a routing pattern of connection matrix, and the second task is to communicate with the hardware. Once getting the right response, it means the routing pattern is correct. You got the provisioning port, you can spot it. Now, the connection matrix is ready to transfer the correct routing patterns to the communication bus channel. And we are ready to fire up our Minicom or OpenOCD to control the target hardware now. This slide is just to justify why the UART and JTAG are widely used as a provisioning port for embedded system, but not the I2C or SPI. Nothing special. We just skip it here. And this slide is still making the justification, but we just stick to the UART and JTAG as our provisioning port. Now, let us go a little bit further. In order to build a hardware hacking machine in year 2005, I need to build a complicated FPGA board. I need to manage the clock recovery process to get correct data. I need to ensure all the timing logics are appropriate and all the rest of the complicated things in year 2005. However, in year 2017, EDA tools become more and more friendly. Embedded hardcore getting more and more common, but softcore still resource intensive. In other words, it's easier to develop high performance signal level hacking machine in 2017, but the entry barrier to build this is still quite high. So the question right now is there any alternative? to let us to build a low-cost version or even simpler version of this hardware hacking machine. Yes, the Evilsploit is the guy, and this is the system block diagram of using Evilsploit to implement a low-cost hacking machine. The only way difference of this version of the hardware hacking machine is it unable to perform active attacks such as signal injections to the target hardware that you want to hack. This is just a graphical representation of the system diagram. Other than the hardware hacking machine, the Evilsploit can also be used as a side channel assistive device. And this is the system diagram to show how Evilsploit can fit into the place. The key point here is SCA needs to process huge number of the samples, and the capacity of the sample is limited from the SCA tools itself. So we need Evilsploit to spot and trigger the sampling process at the right place. This is graphical representations of the block diagram. And other than SCA, the Evilsploit can be used as a FI assistive device, and this is the system block diagram to show how it can be done. And this is the graphical representation of the system block diagram. While we're going a little bit further, Evilsploit can also be used as a QEmul assistive device. In this case, JTAG works together with QEmul to create the context for emulations of the code snippet. By going even more further, the Evilsploit can be used as a static analysis assistive device. The main objective is to automate the process of firmware analysis for the embedded system. So you can analyze a huge number of the firmware. This is an overview of the rear board. As a summary, connection matrix has bridged the gap between the bus identification and the bus manipulations, and it allows higher automation level of hardware hacking process. Now we come to the demo time. So in demo 1, we are going to show the UART pin finding and control. In demo 2, we will see the JTAG pin finding and control. For demo 3, we show a type of the encryption standard which we call it SM4 cracking by using the Evilsploit as the SCA assistive device. The target is a software crypto, and the crypto process takes 0.5 milliseconds to complete the process. And Chui is the SCA tools that we selected, but we only use for the sampling capturing. We use our highly optimized MATLAB script to crack the secret key of the SM4. And in demo 4, triple dash cracking by using Evilsploit as the SCA assistive device. The target is a hardware crypto. The crypto process takes around 27 microseconds instead of the longer process in the software crypto. And we use Evilsploit in the same way again. So in this hardware crypto, it involves a messy signal tuning process which will take a longer times than the demo 3. And we still managed to crack the secret key finally. For anything further about the live demo of this cracking process, please visit our Asana sessions. In asynchronous sessions, demo 4 will not be included due to the time-consuming issue, but we'll show a little bit more detailed video. So, as a takeaway, try to imagine with Evilsploit, you can manipulate the jet tag without knowing what actually the TDI, TDO things is. So let's start with the demo. We start from demo 1.
Hello. Let me show the demo to you. This is the first demo. We use Evilsploit to find the UART pin from a total of 16 pins of the target board. We are going to find the TX and RX pins. So you can send and receive the data from the target board. This is our software for Evilsploit. So let's start. Oh, no, we find the TX is on the 30. Then we find the X pin. The X pin is on 9. Then I set the calibrated return command to the target board. You see the log from target board, please login. 还有一个还没有放完啊
Now we come to the second demo, which we try to search the UART pins.
This is the second
Pcam.
demo. We are using Evilsploit to find the UART pin from the test points on an IP camera mainboard. We use Evilsploit to find the UART pin from the mainboard. We are going to find the TX and other pins, so you can see the bootloader after we find the pins.
It's going to issue the commands. And then we'll start the whole process.
TX is on the line 5. And then we find the X pin. Oh, X is on the line 9.
The process time is a little bit faster than the previous demo is because the pins that we are going to brute force is quite
We can try the
than
password.
first one because we can spot the UART pins in the first place.
Then you see the bootloader.
So after that, the pin finding is completed, then the boot log will show. You no need to change, you no need to dismantle the bus identifications things, and you change your combinations of the cable connections to the something like Adafruit to see the boot log and control the things by using the UART connections. You can run it by itself.
This is the third demo. The Evilsploit is going to find the JTAG pin from a total of 10 pins.
You can see that they got a lot of the wire being connected to the target connectors, and this guy will never care about which cable is going to connect to which pin, and they got no color at all for the jumper cable that's being used in this. So once everything hook up, then let's see how the system works.
Or start.
it will take around 100 seconds to complete the whole process. Is there any pin found?
找了，看见了。怎么了？这么慢？Oh, no, we find the TDO, TCK, TMS, and TDI. Now we can debug it with OpenOCD. Let's jump that. We can send the OpenOCD commander, and with the config field, then you can see the target board is with a microcontroller from ST. Then now we can use MDW commander to see the memory content. You see it.
And for this time, we will try to search the JTAG pins from PM3 boards.
The PM3 is a well-known FRD security hardware tool. It has JTAG connection available on the main board. Now we use the combination of Evilsploit and UI JTAG to play around with it. Just keep. Now we find the TDO, TCK, TMS, and TDI. Then we use detect. You detect to find the edit code. Use the detect command, and now we got the edit code.
You can do it directly. You don't need to do anything further. Now is the turn to show how we use the Evilsploit as an assistive tool to crack the SM4 crypto.
SM4 is a encryption standard like AES. Now we use Evilsploit as an authentic tool to perform side channel attack. We use chip whisper as a assay tool. The Evilsploit is sampling as the right tracking point. And then we use the trance, and we use MATLAB to track the key of the SM4. We need about 100 trans. You can see that in the end of the right key. And this is a photo of the real trans, and this is the CP result when we are tracking the SM4 key. It's first of all S-box.
This is in fact, we use the correlation process to ensure the key is correct or not. Now we come to our third demo, which we crack the triple dash encryptions, which is implemented in hardware methods. So let's see the demo. It's a little bit harder, but with a proper hardware setup and highly optimized scripts, we still manage to crack it. This is a smart card. This video will show how we complete the capturing process in the smarter way by using the Evilsploit as our assistive tools.
We need about 6,000 chances.
We cannot do the live demo here is because since this is the hardware implemented crypto, we need around 5 hours to complete the capturing process. So once the capturing process completed, we just skip it and then we just fire up our MATLAB scripts to complete the attack process and regenerate the secret key from the hardware crypto.
When attracting the key, we use the 6,000 chances capturing from the Evilsploit and Whisper. Then we run the tracking the Xbox.
We in fact take a couple of minutes to complete the whole process. We just fast forward.
You can see we already have the key 1. And then we're attracting the key 2.
So in this place, both of the key has been recovered from our SCA attacks to this smart card. I mean the triple desk key. So that's all of our demo. Q&A? Any question? Yep.
So, maybe I missed that, but what exactly is the role of Toolkit in the key extraction process? You briefly asked the setup, and then you went over your MATLAB instructions, scripts, and stuff like that. But how is the Toolkit helping you in the process?
The toolkit is just to help the SCA things to spot the exact point in order to start the sampling process to get all the samples to fit in to a limited space of the buffer. We know the chip Evilsploit is just an open source hardware and it's got no much buffer to fit all the samples. Okay. So, for any further question, then we can go to the wrap-up room.
Thank you.
Thanks to attend our talk.